Good morning, ma. Students, good morning. Am I audible? We'll wait for 1 minute and we'll start the session. Okay, what we were discussing in the previous class, do you remember? What we were discussing in the previous class, ma, in context section 7. So before your mid semester, this is the last context session, right? So we have seen PGP configuration examples, right? How to verify, configure, and verify the PGP sessions, both ePGP and iPGP. After that, how to examine it. What is the next top self feature? All those things we have seen in the previous class. Fine. So we will start with today's class. Before that, I'll share my screen. Hope my screen is visible. Kindly confirm. Is my screen visible? And that. Okay. In today's class, we'll be saying the PGP state machine, that is how to establish the session. Okay. For that, we'll be saying uh, af- after the three-way handshake, TCP three-way handshake, once it is completed, so once the three-way handshake is completed, PGP will be moving on to the own state machine process. So for what? In order to establish and maintain a session between the two routers. Fine. So this process will ensure both the routers will agree on certain parameters, okay, before exchanging the routing information. So the first one is idle state. This is the initial state. Starts with an initial state, that is the idle state. The router will be looking for a valid route in its routing table to reach the corresponding neighbor. Okay. The second state is if any route is there, it will take it. If no route exists, the session cannot proceed. Okay. So if the route is formed, if I have a route, the router will do the transitions in order to make the connection between that route. Okay. The second state is connect state. So the router will be confirming the connectivity to the neighbor. Fine. So the TCP handshake is already completed at this point. So the router can able to send the open message for initiating the connection. That's the third one. That is open send state. So open message will have the session parameters like what is the version, what is the ACE number, what is the hold time. All those things will be there in the parameters. So this formally will be requesting to establish a peer connection, peering relationship. Okay. And the fourth one is open confirm state. So if the neighbor is also responding with a matching open message, both the routers will confirm the parameters. So the router will agree to move forward, right? So if no valid response is received, the router transitions will be given to the active state. Okay. So active state, if it goes to the active state, it will attempt to re-establish the connection. So the next one is established state. So established state, we'll be saying that is the final state. So idle is the initial state and established will be the final state. Okay. And also it is the most important state. Why? Because your peering will be established successfully between the neighbors in the established state. So the router can able to exchange PGP update messages. Okay. So it will carry actual routing information, right? So the PGP will can monitor, maintain, anything can be it can do once the session is established. Okay, so this is actually the PGP state machine. So PGP state machine, it has a structured step-by-step states. Okay, so only after reaching the established state, the routers can begin to exchange the routing table securely and also reliably. Okay, we'll see each and every state in detail. Already I've told you the initial state is the idle state. Okay, so once you enter the command neighbor remote as, so this is actually the command, right? So once this command is configured, PGP will be immediately it will start the idle state. So it starts with the idle state. So what your router will it will perform a route check. So route check, the PGP process will looks for a valid route. So where it will be looking, always it will look in the routing table in order to reach the neighbor's IP address, right? So that is the idle state. So idle state should be for few seconds under normal conditions. So under the normal conditions, it will be there in few seconds. So if there is a failure, if it is a failure case, if no valid route exists in the routing table, so PGP will remain stuck in the idle state and it will not proceed to the next state. Fine. That is the initial state. Initial state, once I give neighbor remote as command, it will look for the route in the routing table. It will go for the few seconds in the normal duration if it is a normal condition. If not, if there is no valid route in the routing table, so it will stay there. It will stuck in the idle state itself. It cannot proceed to the next state. Okay. So what is the next state? The next state is the connect state. The second state is the connect state. Okay. So if a valid route is found, the PGP from the idle state, it goes to the connect state. Okay. So the transition occurs when I'm getting a SYN plus ZAC. The SYNAC is received, the three-way handshaking mechanism is done, right? Always the client will be sending a SYN. For this SYN, we'll be getting SYN plus ACK. And for this SYNAC, ACK will be transmitted. So this is your three-way handshake, right? You would have studied in computer networks itself, right? So SYNAC is received, the completing, it completes the three-way handshake, right? So once the TCP established the session, the router can generate a open message. Now it can generate the open message. So the open message will be sent to the neighbor. So it will be moving it PGP into the open states. From the connect state, it enters into the open send state. That is the next state. Fine. That is your open send state. From the idle state, it goes to the connect state. Once it is connected, it goes to open send state. Fine. So after the router sends the open message, the PGP session transitions will be into the open send state. Okay. So this means the key parameters, everything that is the version, autonomous system number, the router ID, hold time, everything will be shared. That will be acting as the key parameters. Okay. So the router will wait for a matching open message from the neighbor. So if the neighbor responds correctly, the session moves into the open confirm state. From the open send state, it goes to the open confirm state. Okay. And the next state is active state. So if the router does not receive a valid open message within 5 seconds, this is the threshold time. If it is not getting the response within the 5 seconds, this transition will be into the active state. Okay, so active state, in this state, the router actively will try to re-establish the TCP connection. So TCP connection with its neighbor, right? So frequent active states. What does it mean? Frequently, I'm getting an active state. So it indicates the problems, right? There may be a problem with router issues or wrong neighbor IP or mismatched configurations. So all these frequent active state will give you the problems indicating all these things. So if the TCP session succeeds, the router will be resending the open message and it moves forward to the from the open send state to the open confirm state, or else it goes to the active state. So active state, it gives certain problems. It indicates certain problems. Okay, so what is the next one? The confirm state, right? So when a valid open message response is received in time, the session will move to the open confirm state. Okay, so both the routers agree on certain parameters. So what are the parameters? Just now we have discussed regarding the parameters. What are the parameters? Parameters, right? PGP version, autonomous system number, router ID, and also what is the hold time. So these are the parameters, right? So these are the parameters. So they'll be agree on these parameters. The router will try to begin the scanning, and also it evaluates the routing table. So it determines which path will be the has to be advertised to the neighbor. So if no issues are occurring, the session moves to the final state. What is the final state? That is the established state. So the final state is the established state. So after scanning and selecting the valid paths, the PGP transitions will be moving into the established state. So PGP neighbors can now exchange the routing information through the update messages. Okay, so this is the final state, and also this is the stable state. Okay, so stable state in the sense the peers will be active and the routers, everything will be advertised. So the PGP state can be checked using which command? Show IP PGP summary. Okay, so this is the one which is in order to validate or verify the connection. Okay, so starting from this is the state mission. It starts with the item, connect, open send. If there is a problem, it goes to the active state and tries to re-establish the session. Okay, it will try to re-establish. Okay, if it is okay, it goes to the open confirm state. So from the open confirm state, goes into established state. Okay, any doubts as of now? Any doubts, ma? Students, do you have any doubts? Ma, shall I proceed? Do you have any doubts? Are you there in the meeting? Only one student is always responding. What about others? Are you there in the meeting? Kindly confirm. Very good. Out of 55, I'm getting only 2 response. Now we'll see PGP session resilience. So that can be done with the help of loopback peering, right? Routers can establish IPGP sessions, IPGP sessions using the loopback interface. In the previous class itself, we have seen loopback interface address, right? So with the help of loopback interface address, they can establish IPGP sessions instead of physical interface addresses. Fine. So what is the advantage of loopback addresses? So this loopback addresses will be remaining active as long the router itself is operational. Okay, so the PGP sessions, it will be staying up even if the physical interface fails. Okay, this approach will try to increase the reliability. So how come it improves the reliability? By decoupling the PGP sessions from the physical links. Okay, so it tries to reduce the risk of session drops due to interface issues. Okay, so that's the reason it is widely adopted in enterprise and also service provider networks in order to provide the high availability of IPGP sessions. So this is an example where we have two autonomous system numbers. One is AS65100. In that, we have one router, R1. Okay, so R1 is connected to R2 in the autonomous system number 65000. Okay, so inside autonomous system 65000, we have two routers. One is R2, another one is R3. So R2, R3 will be connected by IPGP, right? So instead of peering via physical interface, we'll be using physical interface IPs. R1 and R2 and R3 will establish IPGP sessions. So this will be done with the help of loopback address. Okay. So loopback phase peering, it prevents the PGP session drops, right? If the physical link or if any of the interface goes down, there will be so if any of my physical link or interface goes down, there will be a problem. In order to avoid that, we'll be going for loopback address. So what will be the loopback address? We'll be using the address 192.168.2.2, and in this router, we'll be using 192.168.3.3, right? So this will give you the resilience. So the session will be staying up as long as there is any valid path between these two routers. So IPGP becomes more stable and fault tolerant. So continuous routing will happen inside the autonomous system. So our R2 and R3 will be configured to form an IPGP session with the help of loopback address rather than with the help of a physical interface. Okay, physical interface IPs. So this makes the session independent of individual interface failures. Fine. So I can use the next stop command. So in this example, so see here, this is the configuration will be done on router R2. The first one is router PGP 65000. It starts a PGP process under autonomous system number 65000. So there is no neighbor. So no neighbor. 172.116.23.3. So it removes the old neighbor configuration. Okay, so whatever the physically that has been, this is a physical interface ID. So whatever that has been given already, that will be removed. And I'm adding a new neighbor, that is neighbor 192.168.3.3, remote as 65000. So this will try to establish an IPGP session with R3. So this is the IP address of R3. So R3 with the help of loopback address. So this is the loopback address. Okay, since both routers are in the same autonomous system number, this will be creating an IPGP session. So the next one, we say neighbor 192.168.3.3 next stop shell. Okay, this ensures R2 will try to advertise itself as a next stop when sending the routes to R3. Okay, this will be avoiding the router problems where R3 might otherwise try to reach unreachable. Okay, uh, this problem already next stop cell we have seen in the previous class itself, right? So this configuration will be done on R3. So the router PGP 65000, it starts a PGP process under autonomous system 65000. There is no a neighbor. It removes the old neighbor configuration and I'm adding a new neighbor. So this remote as 65000. So this command is not used here. Why? Because R2 will be advertising the routes to R3. That's the reason this is not reflected here. So what is the purpose of doing the next stop cell? So this will be avoiding the routing problems. So uh, uh, if R2 is advertising certain informations, it will tell itself as a next stop. So that if it wants to reach to R1, R3 wants to reach to R1, so R2 will be considered as the next stop, or else it becomes unreachable. In order to avoid that, next stop self is given here. So this is what by replacing physical IP peering with loopback peering, the IPGP session becomes more resilient. Right? So the next one, the sourcing PGP from loopback address. So what is the requirement? So when using loopback interface for IPGP peering, the source IP address of PGP packets, it must match the neighbor IP. Okay, that is the one. So which can be configured on the remote router. Okay, so PGP only accepts the packets from IPs. It explicitly it will be known as a neighbor. That is mandatory, right? So if the packet comes from a different IP, it will be ignored, right? So that's the reason without proper configuration, the PGP sessions remain stuck in the idle state. So we have to use the command x.x.x.x update source loopback 0. Okay, so that the router explicitly sources PGP packets from its loopback interface. So when the PGP peers are configured to use loopback addresses, the source IP of PGP packets must match the neighbor IP defined on the other router. So if the source does not match, the packet will be just ignored and the session will be always in the idle state. Okay, so in order to fix this, we can configure the command neighbor loopback IP address update source loopback 0. So this will ensure the PGP always uses the loopback interface as its source. Okay, this can be make the session stable and also it makes this session resilient. Okay, so we'll see that this is on router 2. Fine. So we'll start with, already we have seen uh, router is being configured, which starts the process. We set the neighbor for R2 in the previous, we have told the neighbor, and also we have configured the loopback address as an IPGP neighbor, and also we have ensured R2 advertise itself as a next stop. Okay, it prevents the routing issues where R3 might not know how to reach advertise the next stop. Okay, so what is missing here? So the neighbor 192, which is the neighbor, this is the neighbor. So instead of physical IP address, we have to say we have to use the loopback address. So that can be set with the help of the neighbor command. Neighbor, which is the neighbor? This is my neighbor. Okay, so I'll say update source loopback. So this will force R2 in order to source PGP packets from its loopback 0 address. What is the loopback address? That is 192.168.2.2. So without this, the PGP packets may use the physical interface IP. This will cause a mismatch, right? And also it is same for this is the summary. Okay, so then we have to see a router PGP 65000. I'll be saying update source loopback 0, right? This is for R3. On a router R3 also we do the same thing. Neighbor This is the neighbor. Our bit set loop back 0. Fine. This will ensure R3 also uses its loopback address 0. That is, what is the loopback address? For R3, it is 192.168.3.3. For R2, it is 192.168.2.2. So without the update source loopback 0 command, the session gets stuck in the idle. So in order to avoid that, there will be a mismatch, and also it will stuck in the idle state. Right? So that's the reason we'll be adding the command to ensure the loopback to loopback peering works reliably. Fine. Any doubts? Any doubts, ma'am? Students, do you have any doubts? Shall I proceed? You're there in the meeting. Abhinas, Aditya, Ajay, Alok, Ananya, Anurag, Arjun, Chavan, Deepak. Rather removing all, I'll just, I can end the meeting. Okay, now we'll see sourcing PGP from loopback addresses, that is ePGP. So this is what the configuration which was done in R1. R1 was in the autonomous system number, all those things we have done, right? So we start with so IP root 192 dot subnet mask, and also we have starting root router PGP. So this autonomous this router is in autonomous system number 65100. There is no right neighbor. We are removing that neighbor and we are adding the loopback address. Okay. And this is actually two things we are adding: update source loopback 0. Okay. So configuring both the things. This is what the one which we do in R2. So configuring the loopback address. Okay. How to verify this? Verification can be done with the help of show IP PGP summary, right? So this we are doing in R1. So the neighbor, it shows the neighbor 192.168.2.2. It appears. But what about the session? The session remains idle. So how many packets received? The packet messages received is 0, message sent is 0. So no successful TCP connection. What is the reason? Reason for idle state in PGP with the loopback address. By default, ePGP accepts peers to be directly connected. So what will be the TTL value? That will be equal to 1, right? So when I'm sourcing from the loopback address, the packets may cross multiple hops. So they are obviously it will drop. Why? Because the TTL will be set to 1. So for ePGP over the loopbacks, you must configure the neighbor IP address, ePGP multiple hop together with the TTL value. So it can ensure the proper static routes to the IGP reachability for the loopback IP address. So R1 and R2. So R1 is in autonomous system number 65100, and R2 it is in the autonomous system number 65000. So this is connected with the Ethernet link, right? You remember that, isn't it? So when R1 and R2 are forming ePGP connection with the help of loopback addresses at the source, the neighbor, and also we'll be using the neighbor command together with the update source commands. If even if they are configured correctly, the PGP session, it stays in the idle state. Why it stays in the idle state? Because ePGP sessions, direct connectivity with the TTL of one will be used. What about the loopback to loopback communication? It requires more than one hop, right? In order to solve this problem, we have to use ePGP multi-hop command. So that must be added. So along with the static routes, we have to use that to ensure the reachability. Fine. Works well within the same autonomous system. But with the different autonomous systems, TTL value cannot be one, right? To fix this value, by default, ePGP sessions, the direct connections will be there, and usually the TTL value will be equal to 1. So when sourcing from loopback addresses, the packet has to travel multiple hops. So the default TTL cannot be sufficient. It will be insufficient, right? For that, we have to enable multi-hop. Okay. So this is what the configuration that is done in R1. We can configure the route. So it is autonomous system. It is in the autonomous system number 65100. I said neighbor. This is what my IP address. ePGP multiple hop, multi-hop. This is for R2. Neighbor IP address. It should accept multi-hop. How to verify this? This can be verified with the help of show IP PGP summary, right? So it is showing the neighbor. Who's the neighbor? It is done on R1. R1's IP address. Who's the neighbor? 192.168.2.2. It is established, right? How many messages are received? 6 messages are received and 5 packets are sent. Fine. So the state is equal to 2. 2 prefixes successfully received. So we have to configure the PGP, ePGP multi-hop when we are using the loopback interfaces for ePGP peering. So this can ensure reachability of loopback IP addresses with via the static routes. Okay, so after adding the ePGP multi-hop command on both R1 and R2, we can successfully transition from the idle state to the established state. This is the one which we have verified with the help of show IP PGP summary, right? So the messages are exchanged between those two routers. 2 prefix has been received. Okay, so whenever the loopback addresses are used for ePGP peering, we have to enable multi-hop. That is mandatory, right? In order to make it reachability of the loopback addresses. Hmm. Now we'll see why PGP security matters. PGP is the internet's backbone. So border gateway protocol, it controls how the data travels between the autonomous systems. So every major IP, every major data center, the cloud provider, it relies only on PGP. Okay. And also originally insecure by design. So when it was created in 1980s, so when trust between networks was assumed, it lacks in built-in authentication, built-in verification, validation, encryption, and all. So what is the impact? And also there is an impact on global traffic. So the single incorrect or single malicious PGP update can even redirect or even try to drop the packets, drop the traffic worldwide. So makes PGP a prime target for hijacking and also for getting things leaked. And even it can be sometimes misconfigured. Okay. And also the fourth one is high profile incidents. Why? Because there was a huge YouTube hijack which was happened in 2008. Okay, so the Pakistan telecom. So Pakistan accidentally they announced routes for YouTube. So offline, it takes it offline globally. And also in 2017, uh, uh, there was a misconfigured routes by the Japanese ISP disturbed the global services. That is global Google services for millions of users. And also recently in 2021, Russian ISB, they leaked the routes, okay, causing traffic redirection, security concerns. Okay, was the major problem. Without PGP security, the stability and trustworthiness of the internet will be at the risk. Okay, we are not supposed to take the risk, right? So we'll see some of the things. So 9 threads, PGP threads are there. First, we'll see each and everything in detail. First one is prefix hijacking. So it occurs when an autonomous system uh, illegitimately it advertises the IP prefix that it does not own. Okay, so the traffic in this case, the traffic can be misrouted to the wrong destination, or even the data can be interpreted. Okay, man in the middle attack can happen. So the packets can be black hole. It can be dropped entirely. Okay, uh, the example just now we have seen the Pakistan telephone unintentionally they hijacked YouTube's prefix in 2008. So YouTube that became unreachable worldwide. Okay, that was the problem which was happened in 2008 due to prefix hijacking. Okay, and the second problem is root leaks. So happens, it will happen when an autonomous system improperly advertises the routes. Okay, which are being learned from one provider or one peer to another provider. Okay, whatever I've been learned from one provider, I'll be leaking it to another provider. Okay, so this will cause suboptimal routing, and also it will cause congestion or partial outages, internet outages. So frequently, it will cause misconfigurations. So this will be malicious leaks even can be possible. So that was happened in 2021. Just now we have seen, right? So the root leak by Ross Telecom. Large scale traffic redirection was happened in the recent year 2021. So prefix hijacking and root leaks will be a security concern, security problem. So this will be critical to protect the internet stability. The main problems will be prefix hijacking and the root leaks. Okay. In addition to that, we have 7 more threads, PGP threads. We'll see. The third one is man in the middle attack. Okay. So attackers announce another will try to uh, announce another ES prefix. So they try to attract traffic that should not belong to them. Okay, so normal prefix hijacking, that will not be a one. So they'll be making the black holes traffic. So the MITM attackers will try to forward the intercepted traffic to the correct destination. Okay, after capturing it. So it uh, enables eavesdropping on sensitive data or traffic modification. Traffic modification in the sense altering packets in the transit, right? Or else injecting the malicious data, a malware, or false information. Okay. So all these things, the data can be theft or the data can be even dropped when attackers try to intercept traffic without causing outages. That was the third problem. Okay. And the fourth one is denial of service. Even denial of service can be done with the help of PGP. So when attackers overwhelm PGP routers with excessive or malicious traffic, they'll have flooding problem, right? So flooding the routers. So the flooding the routers with for fake information, uh, malform PGP update messages, everything will make high traffic in my network, in the PGP network, in the autonomous system. And also it forces the PGP sessions to reset, which terminate the peer connections. And also it disturbs the routing. Okay. So routing stability will happen, loss of connectivity happen, can even spread outages quickly across multiple networks. So the large scale DOS attacks will target the ISP routers. Okay, so this leads to widespread internet disruptions. So both the things, prefix hijacking and the route leaks, these threats, it will show how the attackers can exploit PGP for the disturbance or even for the traffic manipulation. Right? Any doubts? Any doubts, Ma? Do you have any doubts? For each and every time, should I want to call your name to get the answers, Amma? Now we'll see the next PGP threat. The next threat is PGP session hijacking. Okay, so the weak authentication exploits weak authentication or lack of security between the PGP peers. So if an attacker, if a attacker is taking over an existing PGP session and he's trying to inject some malicious routing updates. So many legacy of TCP sessions, they rely on TCP. Okay, legacy PGP sessions, they rely on TCP with weak or optimal MD5, message digest 5 authentication, which is outdated, which will be outdated and also which will be vulnerable, right? So unauthorized prefix advertisements will be there. So traffic redirections, manipulations, black hole will happen. So the trust will be compromised in the inter-EAS routing with the help of session hijacking. Okay. And the next one is route flapping. So route flapping, it occurs when the router announces or withdraws any prefix. Okay. Repeatedly, if it tries to announce or if it tries to withdraw the prefix repeatedly. So this will cause the misconfigurations. This makes it unstable links or even the malicious intent. So high CPU and memory usage will happen on the routers due to constant recalculation will be done at the router side. And also the routing instability will happen. It delays the convergence and also the packet loss will happen. So the packet loss together with the jitter will affected for the end users, right? This is the problem which happens due to route flapping. So the next PGP threat is configuration and policy errors. So the human errors, human mistakes, even will be affected. The most common cause of PGP problem. So accidentally announcing a full routing table to the peers. So they should not receive it, but accidentally we are trying to announce a full routing table. Okay. So what will happen? It will misconfigure the filters. route maps, the prefix, everything, the prefix list can be unintentionally leak a large set of prefix. Okay, so widespread of routing leaks will happen. So the leading, all these things leads to congestions. Okay, it can even trigger cascading instability across multiple autonomous systems. Okay, and the next one is cryptographic lack of cryptographic validations. So the PGP does not verify whether an autonomous system is authorized or not. So whether this autonomous system is authorized to advertise a prefix, this will not be validated or verified. So this protocol, the protocol is trust based, right? So it should be trust based. It should be it should not be vulnerable to inject or impersonation should not be happening, right? So in order to solve this problem, we'll be using RPKI, that is Resource Public Key Infrastructure. This is a cryptographically validating the prefix origins. And also we can use PGP-SEC. It is an extended PGP with path validation. So the problem was this adaptation is incomplete and uneven. It is uneven. So vulnerabilities still it is existing. Okay. So this is the another problem due to the PGP. So the last problem that we are going to discuss is traffic analysis and metadata leakage. So traffic analysis, even if no malicious route hijack occurs, the PGP will be making an announcement themselves. Sometimes they'll reveal sensitive information. So attackers, the researchers or competitors can know the network relationship, who's peering, okay, what is going, who is buying transits, everything will be advertised, right? And also the growth or the shrinkage will happen. The network's global presence will grow or shrink. And also there is a weakness in the routing policy. Why? Because which could even exploit certain things. So in order to facilitate the target attacks, so this will impact the target attacks. This will advertise certain critical infrastructure dependencies, right? So these are the major problem with the traffic analysis and the metadata. Everything will be exposed. Sometimes the sensitive even uh, there should be certain sensitive informations to be revealed. If I want to uh, make it as a router to forward the packets from one system to another autonomous system. Okay, this cannot be avoided. So these are the list of PGP threats. So we have seen different 9 different categories. So the first one is prefix hijacking, if you remember. The next one, the route itself will be leaking, or else man in the middle attack will happen. Okay. And the next one, denial of service. The session can be hijacked. Okay, prefix hijacking, session hijacking. Okay, the next one is route flapping. Humans make a configuration and policy errors mistakenly. Okay, lack of cryptographic validations. For that only, we'll be going for PGP-SEC. Okay, and the last one is traffic analysis and metadata leakage. So these are the different PGP threats that should be addressed properly. Fine. Any doubts?
No, ma'am.
Now we'll see uh, some of the examples. So the first one is threat. The first threat is prefix hijacking. What is the impact? The traffic will be redirected, or else the packets will be dropping. That is, it makes it black hole. Mad in the middle attack can happen. Okay, so what is the how it can be rectified? With the help of RPKI, or with the help of prefix filtering, or with the help of route monitoring or route alerts. The next problem is route leaks. Okay, suboptimal parts or even outages will happen. There could be a possible of congestion. This can be avoided with MARN, MANRS, or by implementing the PGP communities, or by using AS path filtering on policy enforcement. And the third one is man in the middle attack. So the data theft, traffic interception can happen. So this can be solved with the help of RPKI and PGP-SEC. And also we can have the strict prefix filtering, and also peering with trusted autonomous systems. We can avoid man in the middle attack. And the next one is session hijacking, unauthorized route, or the network takeover can even happen. This can be avoided with authentication option. Okay, instead of using MD5, we can go for authentication options, and we can have the session encryption wherever it is possible. So together with that, we have discussed denial of a service, the router CPU, the memory, the service outages, loss of connectivity can happen. So the root flap dumping can be avoided, or else we can have the firewalls. Okay. So the next one is root flapping. Root flapping, the packet loss can happen. Okay, convergence will be taking much time. So this can be avoided with filtering. Just now we have seen root flap dapping or filtering. And the configuration errors can be avoided. So configuration now errors, even it leads to accidental hijacks. Okay, this can be avoided by strict change management. Okay, strictly monitoring or peer group templates, or with the help of configuration automation, we can avoid it. Okay, certain problems can be avoided. Certain measures can be taken in order to avoid these threats. Right? So root flapping, the configuration problem, the root leaks, accidental hijacks, all these things. We can have root validation tools. And for the metadata leakage, we can go with unnecessary root announcements can be avoided. We can even have a policy to limit the propagation. Okay, so we can avoid the use of private peering wherever applicable. And also we can add control plane policies and also strict change management. This can be a strong operational mitigations towards the PGP. Right? So now we'll see how to give the measures with the help of RPKI, which validates the prefix to autonomous mapping, PGP-SEC, and so PGP and SPGP. So we'll see each and everything in detail. This is actually the control plane. So the first one with the help of RPKI. So this will be validating the prefix to the autonomous system mapping. Okay, so it will be preventing unauthorized autonomous systems from originating their prefix. Okay, so it will try to reduce the radius of announcements. Okay, so the resources will try to create ROAs, that is route origin authorization, with the help of RPKI. Okay, so the prefix P, say for example, I'm taking prefix P, may be originated from autonomous system number X. So this will have the maximum length of L. So the router will be validating this prefix and the autonomous system from the local RPKI validator with the help of RTR protocol. This will be validated. So each and every PGP route on the router will be tagged with valid, invalid, and not found by comparing the root's origin autonomous system together with the prefix to the VRPs. Okay, so it will be publishing ROEs with the help of RIR. Okay, so this will set the maximum length. So it carefully identifies everything, and also it makes us a, it will be standing up a validator, and it will point to your edge routers in order to use the RTR. So it will be adding ROV policy on the routers. So either for invalid, it will be rejecting. So for valid, to try to prefer. Okay. If it is unknown, we can accept, but we prefer. So all these things can be provided in ROB policy. So we can monitor with the help of the alerts. So this can be integrating with the ROA changes into change management. Okay. So the next one with the help of PGP spec. Okay. RFC 8205, it will be adding as a cryptographic AES path validation. So AES path tampering can be avoided. It can remove AES hops for interception. So it complements our RPKI. So this will be verifying how the route is traveled. Okay, not just who originated, and also how it is being traveled. Even that it will be verified. So each autonomous system will be propagating a route. Okay, with the digital signs, it will be updating a chain of signatures when it travels. So the receiving router will verify that it verifies each autonomous system on the path actually forwarded the route it claims. Okay, so this will have the RPKI certificates for validating their signatures. Okay, so we can validate it. Once it is validated, it can be given to the next router. It can be propagated. Okay, so it can be announced. So it maintains RPKI, PGP-SEC router certificates, and also it keeps the keys rotated and also the keys as a secure one. So strong path integrity can be given with the help of cryptography. Okay. So this will try to reduce the risk. And the third one, so PGP and SPGP. So this will be acting as the early security protocols or early security proposals. Okay, so both will try to secure PGP before today's RPKI, and also the PGP SEC directions were standardized. The first one is SPGP, strong crypto for both origin and path. SOPGP, it is a lighter approach which focuses on origin validation and also the autonomous system relationship information distribution. Okay, so yes, PGP, the PKIs will be public key ownership together with the root assertion, everything. They'll be using the signatures along with the path. So SOPGP, this will try to separate the security information from the PGP updates. So this will be validated whether the autonomous system is okay. It is a right to send the path using a signed ES topology database. So if so, it will be permitted. Okay. So this is how it will be reducing the risk. So with the help of our PKI and also ROV, we can publish ROAs. So where we can enable origin validation, and we can have the ROV policy. These are the policies we can set in valid to reject, valid to prefer, and unknown to accept and de-prefer. Okay. So even PGP SEC, even evaluate hardware capability and also the partner readiness for high value purity. That can be continuously we can monitor, and we can track the ROE coverage, invalid hits, validator health, the routing anomalies with the help of all these three things. Okay. The next one is data plane security. So data plane security, we have to ensure the packets follow intended paths. So the goal of the data plane security is to make traffic takes legitimate and authorized routes, not diverter through the attackers or misconfigured paths. Okay, so it can prevent packet interception or black hole by malicious actors. Right? And the next one is PGP flow spec. So firewalls, they rule via PGP for DDoS mitigation. Right? So the flow spec will allow operators to distribute the traffic filtering rules dynamically with the help of a PGP. So instead of manually configuring all these things, the firewalls can be provided on the each device. So there will be a central controller which will be injecting the rules across the network in the real time. Okay. So this will be effective for distributed denial of service mitigation. So you can even block traffic by giving the prefix or even by giving the protocol, port number, packet characteristics. Everything can be updated in the firewall as a rule. So if a DDO is attacked, let's it is happening on TCP/80 traffic. Okay, flow spec rule can drop it. Okay, with the help of the port number. Okay, this can happen. This will be very easy. And the third one is quality of service. So the prioritization can be given for the traffic. So this can ensure the critical traffic like VoIP, video conferencing, or financial transactions. Everything is prioritized over the important traffic. Okay, prioritized as an important traffic. So it can protect key services from the degradation. So say, for example, if I'm taking voice packets, so voice packets will get the low latency. A large file downloads may be rated, will be rate limited, right? So the prioritization can be given based upon the traffic. Okay. And the fourth one is black holing. Black holing is nothing but dropping the malicious traffic. Okay. So it is a powerful method. It is simple, but yet powerful. So we can redirect the malicious traffic to the null route by saying BVN null. Silently, it will be dropped. Okay. So the local black holing can be done, or even the remote triggered black holing can be done. Okay. So distributed denial of attacks, if I want to black hole, I can just redirect. Instead of carrying the malicious packets across the network, we can drop them at the edge itself. So black holing also drops the legitimate traffic in certain things, certain cases. So they should be properly configured. Okay. So the data plane security, it makes sure all the attackers try to misuse routing. So this can be avoided with the help of tools like FlowSpec, quality of service, and black holing. So the operators can detect and avoid the malicious traffic. Right? Any doubts? Any doubts, ma'am? Students, do you have any doubts? Now we'll see how to give the session protection in PGP. Session protection can be done with the help of three things. The first one, TCP MD5, session authentication. So message digest, we can add MD5 cryptographic signatures. Message digest can be added to each PGP TCP segments. So this can ensure only the peers with a correct shared secret can form or maintain the PGP connection. So it will be protecting against session hijacking. Okay, so MD5 it is considered weak when it is compared with the modern standards, message digest. So that we can go for the second alternative one, that is authentication option. Okay, with the help of RFC 5925. So this will be a modern replacement for the TCP MD5. So stronger algorithms. So instead of using MD5, this will be using SHA1 and secure hash algorithm 256. Oh, many more. Okay, the key roll over without resetting the sessions. So that it can give the better resilience against the brute force attacks. Okay, this also limited due to vendor support gaps. So this is a recommended mechanism for the future, but it is also limited. Adaptation is limited. Why? Because due to vendor support gaps. And the third alternative is generalized TTL security mechanism, that is GTSM. So this will try to protect the PGP sessions against the spoofed packets sent from the distant sources. So this will work by setting the TTL. TTL will be set to 255 in PGP packets. So the receiver only accepts packets with the TTL, which is set to 255. So since spoof packets, they will be originated far away. So their TTL will try to decrease before reaching the router, and definitely it will be dropped. Okay, this is very effective. Single hop ePGP sessions, direct peers, uh, if it works on single hop PGP sessions also, it will be very effective. Okay, so but not useful for multi-hop PGP sessions. So multi-hop PGP sessions, usually we'll be setting the TTL value has a multi-hop. Just now we have seen in the previous slides, right? So for that, we cannot use this. So session protection, it tries to secure the PGP peering itself. Okay, with the help of TCP MD5, TCPA, or GTSM. Okay, so GTSM, it is a lightweight check against the spoof packets. Okay, so we can even harden the PGP session against hijacking, resetting, or DOS attempts with the previous control plane and data plane security. Okay, and the next one is monitoring and detection. So monitoring detection can be done with the help of RIPE, RIS, that is routing information service. Okay, and also with the help of PGP MOA for detecting suspicious updates. So RIS will be try to correct the PGP updates from many points worldwide. So the operators can compare what their autonomous system, what they are announcing. Okay, it can be checked with the global internet seas. And also PGPMON, it is similar service. It's the real-time alert. It can prefix, your prefix will be seen with unexpected origin autonomous systems, subprefixes, or even the hijacks. Okay, so we can detect prefix, we can detect hijacks, we can detect leaks, accidentally misconfigurations can be even given. So if my prefix, say for example, if my prefix is 203.0.113.0/24. So it is suddenly seen originated by another autonomous system. So what your RIS will do is it notifies me within a fraction of seconds. Okay, notification will be sent. Okay, within a fraction of seconds. That is the main advantage. Okay, the second one is MANRS, that is mutually agreed norms for routing security. So it is a global initiative. It is a collaborative industry effect. Okay, why? Because it provides a baseline set for practices. It can do filtering, anti-spoofing, coordination, global validation. Everything can be provided by joining MANRS. Operators can commit to transparent security practices. Okay, so it helps to create a culture of trust and accountability in PGP operations. And the third one, with the help of AI/ML, okay, machine learning models can process massive volumes of routing updates, and they can detect deviations from normal patterns. Okay, sudden path changes, prefix, hijacking, the links can be verified. So real-time responses can be taken, and we can identify whether it is hijacked, spam, phishing, surveillance, everything can be provided. Fine. So monitoring detection, these are the tools. We can use RIS, PGP, AMON for the visibility, for checking the visibility. It gives the visibility, and we can build the global security culture together with the AI/ML techniques. Okay, real-time intelligence can be given to detect the hijacking and also the leaks. Right? Then advanced features. Now we'll try to see the advanced features. So advanced features, uh, PGPLS, okay, link state to carry the IGP link state information. So the routers will be flooding topology details. Okay, and the second one is segmented routing. Okay, for simplifying the traffic engineering. So path sharing without relying on LDP or RSVP can be provided. And the next one is extended communities. So extended communities, the PGP extended communities, it will try to carry the metadata. So what is the route scope? What is the target? What is the action? The control route preference, the local exit, remote exit policies, what is the black holing, everything can be provided. And the fourth one is graceful restart and PIC. So prefix independent convergence. So it allows routers to restart without tearing down the PGP session. Right? So these are the advanced PGP features. So prefix hijacking example is given here. So the victim, yes, is a legitimately, it is owning the prefix. Okay. So there is a user, attacker, and you have a internet. Okay. So attacker, yes, it is trying to falsely announce the same prefix as the victim EAS is having. Okay, so there is an internet routing system and there is a user. So some users, what will happen? They'll be misdirected to the attacker's autonomous system instead to the victim. So the victim autonomous system, it will try to advertise its prefix to the internet. Okay, so this will advertise the prefix. What will happen? The attacker, it takes the same prefix. Okay, it will try to use the same prefix and it will advertise it. So the PGP, it prefers the attacker's announcement due to the routing policies, shortest DAS paths or some specific information, specific prefix. So what will happen? All the traffic intended for the victim will be directed to the attacker. So attacker may drop the traffic, modify or reroute. So this is the prefix hijacking. Right? So the next one is we'll see the how our PKI validation is done. So we have our PKI database. This is the validator cache. Okay. So there are two routers, R1 and R2. So it is connected with the help of an internet. So you have resource public key infrastructure. This will be adding the cryptographic proofs of who is allowed to announce the prefix, that to which prefix on the internet. So the prefix owners will be creating ROAs. What is ROAs? Root origin authorizations. So say for example, autonomous system X may be originating the prefix Y up to the length is it. So ROAs will be publishing all these things with the help of regional internet registries. So the validator, who's the validator here? This is the validator which will be fetching and verifying them. So with the help of validated cache, all these things will be stored inside the DB. So the routers don't pull from the global repositories. The router 1 and router 2 will be connected to the local validator. So this is the local validator using the RTR protocol. It will download the current set of valid prefix or origin pairs. Okay, so when either the router receives the PGP update, it will be checked with the announced prefix and the origin autonomous system against the RPKI DB. So each route will be getting a validation state, valid, invalid, or not found. So valid means we can prefer it. Invalid, we'll be rejecting it. We'll be dropping it. Not found, we can avoid the preferring. So after validation, the routers can be propagating only the acceptable routes towards the internet. Okay. Any doubts? Do you have any doubts? Any doubts, Ma? Can you please confirm so that I can move on to the next slide?
No doubt, ma'am.
Okay. So this is an example for root leak example. Example for the root leak. Okay. So we have autonomous system C, autonomous system B, autonomous system A. A is the provider, C is A and C are the providers, C is the, sorry, B is the customer. Okay. So all these things are connected to the internet. Okay. Providers will be sending the routes downwards to the customers, right? Since they are providing. So the customers not supposed to send those information, send those providers route back to the another provider. So in this example, it is happening. So it is getting the route information from one provider and the customer is sending the data to another provider. So the autonomous system number B, it is a customer. By mistake, it receives the route from provider A. So instead of keeping them, what B is doing, advertising those routes to provider C. Okay, so what C will think? C will think that autonomous B is a valid path to reach the network autonomous system number A. So this is a root leak. Okay, so this is called as root leak. So because autonomous system B leak the routes, it should it should not be done. It should not advertise it, right? So that's the reason this problem is called as a root leak. So whenever C wants to send the data to A, it will be it will be redirected to A, redirected through B. What will happen? Sometimes autonomous system may not have the capacity to carry that traffic. So congestion will happen, or else malicious actors can use the root leaks to get the manipulated data, or else the traffic will be taking a longer or inefficient path. So all these things will happen. So this is the root leak example. The next one, the case study is, we have seen the case study is the YouTube hijack, which has happened in the year 2008. The Pakistan Telecom intended to block the YouTube. Okay, they announced a specific route for YouTube IPs. And they leaked the route leak was happened globally and black hole YouTube traffic worldwide. That too for 2 hours. Okay, and the next one, 2017, which was happened in Google. Okay, misconfigurations happened at Verizon, accidentally advertised incorrect prefix. So the Japanese internet service providers like NTT, they accepted those routes. So the Google services in Japan was unreached for over an hour. It was not an hijack, just by mistake, it caused a massive disruption. Okay, and also the recently Ross Telecom leak happened in the year 2021. Okay, the prefixes, thousand of prefixes were leaked. Okay, so due to that, the Google, AWS, Akamai, every routes were for a short time the traffic meant for all these cloud services were directed through Ross Telecom. So serious concerns that happened due to data interception. Okay, so these are the lessons which we want to study. Just now we have seen, right? So in April 26, 2021, between 22:36 and 22:43, this was happened for 7 minutes. Okay, so it was happened for 7 minutes. Lasted only for 7 minutes, but then PGP turns even a few minutes can give a global impact, right? So Ross Telecom identified the autonomous system. So autonomous system identified, which was 12389, started improperly advertising 135 PGP prefix. Okay, so all these routes were propagated to multiple tier 1, that to tier 1 ISPs. Okay, so Tier 1 providers, including Telcom, Telstra, okay, KDDI, everywhere it is propagated. Okay, so 32 prefixes were leaked. So what has happened? For those 7 minutes sensitive traffic, everything is diverted through Rostelecom. Heavy risk was happened, interceptions, avalanche, unintentional data, everything was provided, diverted to Rostelecom. One provider's misconfiguration, it has disturbed entire world. Okay, that was the problem which was happened in 2021. So the traffic impact on internet traffic, direction, redirection, that was a first problem. During that incident, traffic meant for critical services like e-commerce, authentication system, global banking platforms, everything rerouted through Rostelecom networks. So risk of traffic interception, delays, data manipulation, everything has happened. And also extended path loops happened, long abnormal paths. So package entered whatever that has been entered into Rostelecom network. It has traversed more than 60 unresponsive interfaces, right? So that was a major problem. And the third one is partial propagation. So not a complete internet. It preferred these bad routes. Okay, that was the problem because not all ISPs accepted. So they preferred certain bad routes. So overall scope and global impact, it was still dangerous for affected networks, right? So just it happens for 7 minutes. The sensitive financial and security traffic, everything it is redirected, delayed, and even it was exposed, right? So this, uh, if you want to examine the one which was happened in 2017, so this was actually the date, roughly around 74 minutes. So actors with Google and Telecom. Okay, due to PGP routing error at Verizon, incorrect routes is given to Google service. Everything were advertised. So these routes were accepted and propagated by Japanese internet service providers, even including NTT Communications. Okay, so the large portion of Japanese internet traffic meant for Google was misrouted to Verizon. Okay, so users across Japan, they have experienced Google service outages. Whatever the Google services, Gmail, search, YouTube, everything was outaged. Okay, so that was actually another problem, another incident which was happened in the year 2017, happened by Verizon. Okay, so what happened? Just now we have discussed misconfigurations at Verizon. It was last for 74 minutes. Everything was they misconfigured and it is given to Google. All the Google's traffic was redirected to the Verizon. Right? So the result misrouted through wrong paths. This is a simple mistake, right? What is the impact? Impact of this incident? All traffic meant for Google services, it was misrouted because of the incorrect PGP announcement. So the large portion of that traffic was black holed. Okay, so service outages was happened in Japan. Why it happened? Why it has happened? Due to PGP simply trust everything. So it trusts every routes it receives from the neighbors, right? That was the problem. So Verizon did not filter out the illegitimate announcements. Came from some small Japanese ISPs. Okay, so this lack of filtering, it allowed Google prefixes to be advertised like a valid paths with the help of ISPs. Right? So small misconfiguration at Verizon, it affected it also because Verizon is a Tier 1 provider. It affected widespread disruption across multiple regions. Right? So what are the lessons learned? We have to do prefix filtering, okay, and RPKI adaptation is required in order to avoid the global risk. Okay. So future directions in PGP security, so wider RPKI development and RPKI as a service is required, and also AI ML driven detection, anomaly detection. We have to monitor. Uh, we can detect unusual routing patterns in real time with the help of AI ML, and also zero trust approach. That is, don't trust anyone. You have to always verify. Okay, just like that, we are not supposed to trust anyone. We have to always verify. So the routes must be validated cryptographically, or else even with a certain policies, we can verify before accepting it. And also we have to strengthen the global cooperation. Okay, so security isn't just technical; it's about the cooperation, right? Any doubts, Kana? Do you have any doubts? Students, do you have any doubts? Can you please respond? Ma, you there in the meeting? Can you please respond? Do you have any doubts?
No,
No.
ma'am.
Can you please confirm whether you can access the quiz?
Yes, ma'am. We can accept.
Oh, fine. No. So complete the quiz. Don't leave the meeting. Complete the quiz. And I only consider the average. Okay, if you're even missing 2 or 3 quizzes, that quiz marks will be considered to be 0, and I'll be taking the average. Fine. So don't miss the quiz, attend the quiz. Even if you're absent for the contact session, try to attend the quiz, or else the quiz mark will be turned to 0. So for the mid-semester examination, you have the portions from contact session 1 to contact session 8. I'll upload all the slides, annotated slides in the Teams. You can use it for the preparation. Okay, attend all the questions. All the very best. Okay. If you've completed, you can leave the meeting. Thank you, ma'am. I'll end this meeting. Make sure everyone completes the quiz. Fine.
Fine. Thank you, ma'am.
Thank you. All the very best for your mid-semester examination. Do well. Attend all the questions. The portions is from CS1 to CS8.